This video is for Chemistry in the Earth System, Unit 3.1, Ion Formation. Today's essential question is, how does the formation of ions relate to the octet rule? Our first main idea, the octet rule. The elements in group 18 of the periodic table, helium, neon, argon, krypton, xenon, and radon, are the noble gases. Due to their stable outer electron shells, noble gases do not readily react with other elements. The outer valence shell of each of the noble gas atoms holds a full complement of electrons. Excluding helium, which has a duet, each of the noble gas atoms has an outer valence shell consisting of 2 s orbitals and 3 p orbitals. Each of these 4 orbitals contain 2 electrons. Because their valence shells are complete, the atoms are stable. Chemical reactions tend to occur so that the atoms of non-noble elements have a stable outer shell of 8 electrons as well. Since a set of 8 is an octet, this principle is called the octet rule. Notice on the screen here, with the exception of helium, all elements have 8 valence electrons. For example, the atom of sodium holds 1 electron in its outermost valence shell. The next inner shell already holds 8 electrons. So, when a sodium atom loses the electron in its outermost shell, the complete inner shell, which now becomes the valence shell, remains. And since the sodium atom has lost a negative charge, its ion will therefore have a net charge of 1 plus and is written as Na plus. Metals such as sodium typically lose electrons to form a complete valence shell. Therefore, metals usually form positively charged ions. But how does the octet rule affect elements at the other end of the periodic table? This is where the non-metals reside. An atom of chlorine, for example, holds 7 electrons in its valence shell. Therefore, when it gains 1 electron, its valence shell will now have a stable configuration of 8 electrons, and the octet rule is again followed. Nonmetals, like chlorine, typically gain electrons to form a complete valence shell. Therefore, nonmetals form negatively charged ions. Our next main idea, exceptions to the octet rule. There are many exceptions to the octet rule. Transition metals, for example, and there are more, but I want to focus on the transition metals, may not follow the octet rule because they form bonds that don't only include the s and p orbitals, which is the main orbitals that we are concerned with, but they tend to form bonds that involve the d orbitals as well as the f orbitals. A complete outer shell for these elements would therefore include more than 8 electrons. Another exception to the octet rule involves the element helium, He. Helium is a very small atom. It has only 2 protons in its nucleus. So, helium needs only 2 electrons to make a neutral atom. These 2 electrons make up helium's valence shell and give helium a complete, stable electron configuration, which we refer to not as an octet, obviously, but we refer to it as a duet. So, to achieve this configuration and to become ions, the atoms of the metallic elements, again, elements on the left side of the periodic table, close to helium on the periodic table, lose electrons so that their valence shells contain 2 electrons. For example, lithium, Li, has a total of 3 electrons. 2 of these electrons lie in an inner shell. one electron lies in lithium's valence shell. So, to achieve a complete, stable outer shell of 2 electrons, just like that of helium, the lithium atom loses that single outermost electron, and the lithium ion then has a charge of 1 plus. The atom of beryllium, Be, has a total of 4 electrons. 2 are in its inner shell, and 2 are in the outer shell. To achieve a stable valence shell, the beryllium atom can lose its 2 outermost electrons, and the beryllium ion then has a charge of 2 plus. At this point, you should be able to generate a full and appropriate response to today's essential question. How does the formation of ions relate to the octet rule?